The most amazing thing about this image, there's a bunch of things that are amazing. First of all, every dot in this image is not a star but a galaxy. There are 100 billion galaxies at least in the observable universe, each containing on the average at least 100 billion stars. Some of these galaxies in this particular Deep Space Hubble image are at least 8 or 9 billion light years away, which means the light from those galaxies left well before our sun formed. And it meant that since the lifetime of stars like our sun may be 10 billion years, many of the stars in this image don't exist anymore. And any potential civilizations around those stars don't exist anymore, just as if they took a picture of us and saw it 10 billion years in the future, we wouldn't exist anymore. So it's it kind of amazes me to think about that. But the other thing that's really weird, as a theorist, is that there are the same number of galaxies everywhere we look in the universe. If this image had been taken at any other spot in the universe, on average it would look the same, and that's very strange. We don't quite understand that, and maybe we'll get to why that's strange. It may not seem to you that strange that the universe is the same in all directions, but from one end of the universe to the other end of the visible universe, light has just made its way there. Now, nothing could travel faster than light, so that means one region never knew the other region existed. So if regions could never have been in causal contact before now, how come they're all the same? How come the universe is the same everywhere if those regions were separated in time? A big puzzle which we've tried to solve.
Now, Galileo was taught in his studies that the Greeks had a view of mass or of weight, and the heavier thing you were, the faster you would fall. And he was horrified by this because he was pretty sure it wasn't true. He came up with an idea that gravity was maybe a little different than what the Greeks had posited. Almost 300 years later, Einstein looked at that same situation, and in his case, he was thinking about someone falling off a roof. And he thought, when that person falls, they must not feel gravity, because their falling, their acceleration, would be exactly counteracting the effect of gravity, that free fall or weightlessness that we talk about in space. Now, most people had probably had that thought and not made much of it, but Einstein said, I think that must always be true. There must be no situation where gravity and acceleration will not counteract each other. And that led to him developing what we see as his most profound theory, that of general relativity, which involves the curving of space, and it involves making us know where we are if we use our GPS here in Davos. One of the things that Einstein could use his theory to do was to look at how the universe should behave. And when he did that, he got a funny answer. He got an answer that the universe should be in motion. But he looked around and he said, looks pretty still to me. And so he invented a fudge factor, known as the cosmological constant, energy that's part of space that could repel, essentially make gravity repulsive instead of attractive. And so he was able to make space still. In 1929, Edwin Hubble, one of the first observers of the universe, and he discovered in 1929, by looking at objects, at galaxies, that the universe was expanding. And let me show you with a little illustration of what he saw. Nearby objects, they moved a little bit. Distant objects moved a lot, and indeed, the further away you are, the faster the motion was. And when those observations are why we describe the universe as expanding, because they make perfect sense. Turns out it's also what Einstein's theory of general relativity predicted, but Einstein was a brilliant guy, and he got his head around all sorts of things, but that was too far. He couldn't quite get his head around that.
If he'd had the courage of his convictions, he would have predicted this in a sense, because his theory required it. And it changed everything. In science, the conventional wisdom was the universe was static and eternal. Then, with this, of course, if things are expanding, it must have had a beginning.
Using a supernova to go out and measure things further afield, we can think, I guess, a bit about what the universe was doing, not just now, but in its past. Why? Because this object, an exploding star that makes all the iron, or most of the iron in the universe, is so bright, we can see them not just next door like Hubble was looking, but with modern telescopes we can see them 5, 6, 10, even 11 billion years in the past. They're very faint. Their light takes a long time to reach us. And what we found was not what we expected. We expected to measure that the universe was slowing down. Why? Einstein's theory of gravity and your intuition says gravity pulls. Gravity will slow the universe down, just like gravity slows a ball that I throw up in the air. Gravity of everything in the universe will attract everything and slow it down. Instead, what we found when we look back is we found the universe was curving the other way, that it was expanding slower in the past and had sped up over the past 6 billion years. We put it into reverse. Everything in the universe gets closer and closer and closer and closer, and at some point in the past, there has to be this time when everything in the universe is on top of everything else. It's almost guaranteed if the universe is expanding.
The interesting thing is when not only did the Big Bang change everything, because it meant the universe had a beginning, and perhaps that's the one bit of cosmology that's really crept into the public's consciousness. Everyone thinks the universe had a beginning. Some people, unfortunately, in my country think it was 6,000 years ago. But if you think about it, Brian was just saying, you can look at supernovae that are 10, 11 billion light years away. If the universe is 13.8 billion years old, which is about how old it is, you might think that if you look far enough, you'll see back to the Big Bang. And you would in principle. But in practice, we can't because there's kind of a wall. As we look back at the universe, we're looking at earlier and earlier times, as Brian said. Well, back when the universe was about 300,000 years old, the temperature of the universe was about 3,000 degrees. And at that temperature, that's hot enough to break apart atoms, to separate the electrons from the protons, and you produce what's called a plasma. And a plasma is opaque to radiation. You can't see through it. So if we look back further and further, we get to the point where we see the universe at that instant, and we can't look back earlier than that instant because light from earlier times can't get to us. This is a wall. This is as far back as we can see. But it's an amazing wall because, of course, it's a prediction of the Big Bang that radiation should be coming at us from that surface. When we look out almost 13.8 billion light years away in all directions, we see radiation coming at us from that surface because at that moment, when it cooled to below 3,000 degrees, matter became neutral, the universe became transparent, and this image, called the cosmic microwave background radiation, has actually won 2 different Nobel Prizes for the discovery of it, and this image is really a baby picture of the universe. This is, by the way, a projection of that 2-dimensional sphere. If you want to see the non-projected version, it's like this, with us at the center. We're not at the center of the universe, because if we moved over here, we'd see a sphere centered around us over there, and if we were over here, we'd see a sphere centered around us over there. But when we look out, we see this image, and the amazing thing is, in this image, color represents temperature. The average temperature is about 3,000 degrees, and these little variations in color represent variations in temperature, but the variations are extremely small. The difference from this temperature to this temperature is less than 1/1000th of a degree. The temperature of the early universe was the same everywhere, with extreme accuracy, and that is even a bigger puzzle.
Now, I find this image, when you think about it, you're looking out at the center of this. This is a picture taken from Earth, and looking out this way, we see about 13.8 billion years back in time. Looking out this way, we see 13.8 billion years in time. So it's not surprising that that's 13.8 billion years away there. That one's 13.8 billion years away there. So there just hasn't been time in the universe for information to go from point A to point B. But as Lawrence said, if we step a little bit to the side, we see a slightly different sphere. That means that there's stuff outside of this sphere that exists that we can't see. And indeed, with our current understanding, we will never be able to see this because the universe is accelerating, and the light from material out here will try to get to us, but the universe expands faster than it can make it through the creation of space. And so we have a real fundamental question. If I can't actually ever see or know this stuff exists, and it seems like it should exist, is it really there?
Like a tree falling in the forest.
Exactly.
Now, but it's an interesting question. Are we at the limits of empirical science when it comes to understanding the universe? Because if we can't see out here, can we not say anything about what happened here?
So we're here now. We look back in time. The universe is getting smaller and smaller, but it's speeding up in its expansion. Galaxies are getting younger and younger as we look back in time because they've only maybe 2 billion years after the Big Bang. Eventually, we get to a time when there are no galaxies and there are no stars. The universe is a very boring place. And we think that's about maybe 400 million years after the Big Bang. We don't know. This is one of the things the James Webb Space Telescope is hopefully going to help us answer. There's a period of dark ages. The universe is, of course, still expanding during this period of time. So it's becoming denser and denser as we look back in time. Eventually so dense and so hot that we have this wall. There was the idea that the universe, when it was really, really young, or at the time right after the Big Bang, would have inflated or grown exponentially. It would have accelerated in its expansion. As that expansion goes, you would take little quantum mechanical effects on the tiny subatomic scales, and they would suddenly become the size of the universe. And those would be the things that created those ripples in that cosmic microwave background. Interesting story, and I have to admit, I was not
I was going to say, I remember when I was talking about that. Did you believe it?
No, I did not believe it, and I made it a personal goal to go through and show that this story was wrong. To my bemusement and, in some sense, regret, this theory perfectly has predicted what we have seen in essentially every possible way we've been able to measure.
Yeah, but you know, the question, the science is different from religion in importance in many ways. First, it's right, but secondly, it doesn't just tell a story. This story sounds very nice, but as Brian said, it makes predictions, and you need to be able to test those things. That's what determines whether the story is correct. And so, but you might say, well, look, you know, it's all right, but we're not really seeing time back here. We can only see it as far back as this. To really know if inflation happened, we really have to test physics that's happening here. And if we can't see past that point, how can we test those ideas? And the way we can do it is a remarkable facet of the universe. This is one of my favorite images. It's called the Ouroboros. It goes back in many different cultures, at least 4,000 years. And it's a snake eating its own tail, and different animals at various different cultures. This really represents the universe in a real sense, because the universe is expanding. As Brian said, it was much smaller. In fact, before the period of inflation, actually, it's even smaller than our visible universe was actually smaller than the size of a single atom. It's hard to imagine all that matter, all that energy in 100 billion galaxies, each containing 100 billion stars, contained in a region smaller than the size of an atom. It's amazing we can talk about that with a straight face. But that means if we want to understand the macroscopic properties of our universe, we want to understand physics on very small scales, not very large scales. And that's why I, as a particle physicist, got into cosmology, because the way to test the universe on the largest scales is to try and probe matter on the very smallest scales. So one of the ways we can try and probe those very early times in the history of the universe is not to look out with telescopes. This is the Large Hadron Collider at CERN. If you go into Geneva near here and you land at the airport, which is up at the top of that image, you'll look out and see countryside. It won't look like there's anything very special. But underground is the most complicated machine humans have ever built, a 26-kilometer-long tunnel that accelerates protons in one direction at 99.99999% of the speed of light. And when they collide, the energies are such that they locally produce conditions that are reminiscent of the conditions of the very early universe. So if we want to locally create conditions that tell us what the very early universe was like, we need to build large accelerators, and we need to be very bold. The vacuum created in the tunnel of the Large Hadron Collider has fewer particles in it than the space outside the Earth. At the Large Hadron Collider, we're probing times comparable to the age of the universe when it was a millionth of a second old. Okay, that sounds like it's far back. But what is amazing to me is we potentially are on the threshold of having discovered physics associated with the universe when it was a millionth of a billionth of a billionth of a billionth of a second old after the Big Bang. We may be observing the universe now, in a sense, at a time when inflation happened. How can we do that? Because I told you can't see back in time before the universe was 300,000 years old. Well, that's with light. because light can't make it through that early universe. If you want to see back further, you have to look at something that interacts much more weakly than light. It turns out gravity does. Brian showed the gravity that Galileo was experimenting, and gravity seems pretty strong. If you try and get up in the morning to come to this event, it's pretty strong. But the problem is the entire Earth is pulling you down. The gravitational interactions of one elementary particle on another are incredibly weak. Gravity is the weakest force in nature. But Einstein, when he developed his general theory of relativity, told us something amazing. Gravity, as Brian said, is a property of space. The curvature of space is associated with gravity. And that means that you and I are curving space around us because we have mass. And it means when I wave my hands, and as Brian would like to say, I do that a lot, I'm actually curving space, but I'm producing a moving disturbance in space. Einstein predicted, although he actually didn't believe it initially, that when you move your hands like this, just like when I shake an electron back and forth, I produce an electromagnetic wave, a radio wave, or light. If I move my hands around like this, I'm disturbing space, and I produce a disturbance in space. We call that a gravitational wave. And in fact, this room is full of gravitational waves that are going through this room right now. As they go through the room, the size of the room changes, so the length of the room becomes a little less in that direction and a little greater in that direction, but by a very, very small amount. When I wave my hands, I produce gravitational waves that no experimentalist now or like ever is likely to be able to measure because it's so weak. But nevertheless, they're here. And here's a three-dimensional version, since if you like that, it looks more like a snake. This is what a gravitational wave looks like. This is what it does to space. Experimentalists have built another detector to detect gravitational waves. This is the largest detector on Earth to look for gravitational waves. This is in Hanford, Washington. There's another one in Louisiana that looks the same. And it is amazing. What this detector is two long tunnels, each 4 kilometers long, at right angles. And if a gravitational wave comes down, well, the length of that tunnel will shrink while the length of that tunnel will grow. And we can predict that black holes and other colliding objects in our galaxies will produce massive amounts of energy and produce massive amounts of gravitational waves, but in fact, the effect will be very small, so small that the experimentalists who designed this had an amazing challenge. And they met that challenge. And this is amazing to me. Every time I think of this, that people can do this is remarkable. In order to detect the kind of gravitational waves they're looking for, they had to design a detector that could measure a change in the length of that tunnel, 4 kilometers long, compared to the length of this tunnel, that was 1/100th the size of a proton. And they could do it. They built a detector to do that, but they still haven't seen any gravitational waves.
But this year they're coming back online, and we have every reason to believe that when we do the theory, the pen and paper stuff he likes to do, the predictions are now we should be able to discover something in the next couple of years.
Yeah, they've improved the sensitivity of this detector by about a factor of 10 or so, and that means they should be able to see something, but it may not be the first discovery of gravitational waves, because there's another detector, this one here at the South Pole. But this detector is looking up, and it's looking at the microwave background radiation that surfaced when the universe was 300,000 years old. Well, what's that got to do with gravity waves? Well, we think that if inflation happened, this incredibly massive expansion in the early history of the universe, besides producing everything else, it would produce a massive amount of gravitational waves. Those gravitational waves would propagate through the universe, right through that surface of last scattering, as we call it, and they'd leave an imprint on that surface. And in March of this year, we could predict, in fact, I, among many others, predicted about 25 years ago what that signal might look like. What is amazing is in March of this year, this experiment called the BICEP experiment, reported a result that looked identical to the prediction of inflation. And if it's true, that is a signal, that is a direct signal from the universe, not when it was 300,000 years old, but when it was a millionth of a billionth of a billionth of a billionth of a billionth of a second old.
But we should remind ourselves that this stuff is hard.
Yes.
And so this experiment may have actually seen dust bunnies across the universe, little bits of dust, and we're not sure. Irrespective of whether or not it's dust or literally the holy grail of the Big Bang, it tells us that we're getting closer to not discovering it this time, discovering it next time.
If we can probe the physics of inflation, one of the predictions of that physics is that, in fact, most of space is still expanding very fast. Our universe was like a seed that decoupled from that background space that was expanding, but there should be many other universes, some of which are just being born now. If we can test the physics of inflation, we'll turn this metaphysics into physics, because we'll be able to probe the theory, and even though we won't ever be able to see those other universes, we'll be able to make predictions about our universe based on that theory, and if they predict the 50 things we can measure accurately, then the 51st, which we can't see, which is the existence of other universes, is something that we'll be willing to at least indirectly accept. Just like when Einstein was developing, in fact, his special theory of relativity, we didn't know, no one would ever thought we'd be able to see atoms. But everyone knew atoms existed because of all the indirect evidence. So this will be an amazing result if it's true, because we'll be able to probe the metaverse, not just our single universe.
Let's go back to our universe now. Back to this picture. Now, I told you that's 1/13 of the sky. There's about 20,000 galaxies in this single image. Each one of those galaxies has roughly 100 billion stars. And what we know is that probably 20% of those stars have something that looks like a habitable planet on them. That's something that Kepler has figured out. So how many stars are out there? Well, a lot, and you can imagine. You've got all those galaxies and stars in that image, so there's 13 million pictures, each with 20,000 galaxies. That's 260 billion galaxies in the visible universe. The fact that it's finite is because the universe isn't that old. Each one of those has 100 billion stars, and so that gives us a lot of stars. So people like to ask me, is there life out there? I don't know. I know there's a lot of chances for it. And let's compare that to something maybe we can relate to here on Earth, grains of sand on Earth. So the number of grains of sand on Earth is not terribly well known. This is a reasonable estimate. And
where did you get that?
Wikipedia, where else?
Okay, good.
So there seems to be more stars in the universe than there are grains of sand. And I should say, I think we actually know the number of stars in the universe better than how many grains of sand
We
there
do.
are.
In fact, actually, this is an elementary physics problem that I give to my students, because if you work out order of math, any of you should be able to estimate the number of grains of sand on Earth. Even Brian should be able to estimate that. And if you actually just do a rough estimate, what the amazing thing is, rough estimates of thinking of how many beaches are on Earth give you an almost equal number.
Yep.
Okay, I don't know where this number came from. And the important thing about that is that we don't know this number well enough, so order of magnitude estimates don't work. We really don't know, in fact, whether there are more grains of sand on Earth than there are stars in the sky, which is another mystery.
Similar numbers.
Yeah, similar, but it's a mystery that keeps poetry going.
All right. But the whole point of astronomy and science is to go and start answering questions like that, and that's one of the things we are going to be able to contemplate over the coming decade.
Now, as we think about life in the universe, one of the amazing things is learning about life here on Earth. So we've been talking about the vastness of the universe, but our ideas of life on Earth have been changing dramatically. Every new week we discover new aspects of life here on Earth, or life potentially nearby. These are electron micrographs of what are potentially the oldest fossils from Australia, of course, the oldest fossil life on Earth, which may be almost 4 billion years old. The Earth is 4.5 billion years old. That means life potentially originated on Earth about as soon as the laws of physics allowed it to. It's a big mystery, because bombardment by asteroids and comets on Earth would have evaporated oceans until Jupiter managed to gobble many of them up or kick them out. And it would have taken about 300 or 400 million years for that to subside. And within 100 million years, apparently life arose on Earth, which is amazing, because life is so complicated. But the interesting thing is, well, we're discovering, what we're realizing is that life is much more robust than we ever thought. On Earth, we're not only discovering older fossils, but we're discovering that there are things called extremophiles, that there are forms of life that can exist on Earth in regions that we would have never thought possible, in boiling water, in acid, deep underground. And that gives us hope. If we go to places like Mars, that maybe we'll find life there, or potentially, here's one of my favorite pictures of the rovers on Mars, potentially in icy moons of Jupiter or Saturn, it turns out there's liquid water under that ice. And we may find life there. And what's interesting is, if we find life on Mars, well, would that be an amazing discovery, because we'll discover an independent source of life in the universe, which would suggest life is everywhere? Well, hold off. Because we discovered those extreme forms of life can exist in environments so extreme that, for example, if there were life on Mars, and microbial life, and a asteroid hit Mars and knocked a rock out containing life, it could make it all the way to the Earth, and that life could survive. It means no planet is an island in our solar system. If we discover life on Mars, the interesting question will be, is it our cousins? Because if there's life on one planet, it could easily be transported to the other. So we are, in fact, much more optimistic that we may find life or extinct or extant life on Mars or perhaps in other parts of our solar system, but we don't know if it's independent. The big question is, are there independent sources of life? But the other great discovery is, as Brian said, we've discovered lots of planets around different stars, over 4,000 now planets from the Kepler satellite.
Huge numbers, yes.
And as a theorist, I'm proud to say, once again, that we were wrong. Because we thought there were certain things that could never happen, like no planet could ever orbit a double star system. It was just not classically a stable orbit. We discovered planets orbiting double star systems. So there are many more planets, many more solar systems. There's much more in heaven and earth than was dreamt of in our imagination. And that means there are many more sources of potential life. And therefore, I'm quite optimistic that life is ubiquitous in the universe. Is there intelligent life? We don't know. We don't even know if it's on Earth.
When you look at these, when we look at the possibility for planets, because we're discovering so many of them, with the next generation of telescopes, we're going to be able to look at them and literally see their sun's light shine through their atmosphere. And when the light shines through the atmosphere with the giant next generation of extremely large telescopes, 3 being planned right now by various places around the world, we will have enough information to see the fingerprints of whatever's in that atmosphere. Ozone, for example, which exists on Earth largely due to the vast quantities of life here. Who knows what we'll see? Maybe CFCs or something else indicating intelligent life.
This actually looks like those early forms of life. It's actually the first form of synthetic life ever created. Craig Venter, my friend in California, basically produced a genetic sequence on a computer, which then built that genetic sequence, element by element, and inserted into bacteria and created a new life form that had never existed before. It's important when we think about life in the universe to wonder whether the life that exists evolved in conditions like that, or maybe by advanced civilizations was created. And that means another opportunity for life. But those advanced civilizations would have to be advanced. That means they'd have to survive for a long time. And that's an open question, which we may get to, because the key question is, clearly there's life on Earth, maybe there's life elsewhere, but how long will that life survive? And we want to talk about the future of the universe now.
Fermi thought about the problem that we've been talking about. Is there life out there? And specifically, is there civilized life? Now, civilized life is going to realize, like our own, that our sun, over the next about 500 million years, nuclear reactors are going to get stronger and stronger and hotter, and eventually our oceans are going to boil off in several hundred million years. So we've got a lot of time to figure out if we can go interstellar, go to another star. The nearest star you can't see here in Davos, but if you come down to visit me in Australia, you can. And that star is Alpha Centauri. It's this star right here. It's one of the brightest stars in the southern sky, and very conveniently it points to the Southern Cross. That's how most of the children in Australia know it's there. Now, 4.3 light years is how far away Alpha Centauri is. So that's a long ways. That means it's 300,000 kilometers per second. That's the speed of light, traveling for 31.5 million seconds per year for 4.3 of those. It's a lot of kilometers. But with our fastest spacecraft that we have now, like one that's going out to Pluto and will be rendezvousing, a very exciting trip this year, it would take 26,000 years to get to Alpha Centauri. That's a long time, but imagine we can do cryogenics or just have a big party place where people live for 26,000 years.
One big Davos party going out there. Yeah.
That means when we get to Alpha Centauri and we find one of the planets there, we will live there and, build up our civilization, probably chash the joint again, and want to move on. And of course, we will have the technology to move on. So when we look further afield, how long does it take to move everywhere in our galaxy? Well, it turns out about 600 million years at the speed we can go right now. But the universe is 13.8 billion years old. So this is, factors of 20 or 30 more time to populate the universe. So imagine that there is some civilization that has figured out how to travel interstellar over the lifetime of the universe. Then that civilization should have been able to populate every star in the galaxy. And Fermi looked out, and he had access to Roswell and stuff, and he said, I don't think we have been visited by aliens. And then he concluded that would be evidence that no civilization has yet managed in the history of our galaxy to be able to travel interstellar.
He said, if they were there, where are they? Why don't we see them?
Yeah, why don't we see
them? And you know, it's one of the most fascinating questions. There are many reasons why, in fact, you might imagine civilizations would make it. One of them may be simply that advanced technological civilizations don't survive very long. Davos is here to try and make our civilization survive a little longer, but as obvious, there are major impediments to that, as we talk about this weekend. Maybe our civilization won't survive, but the question is, what will happen in the long term if our civilization is somehow smart enough to survive? And the point is, ultimately, the universe is not a very hospitable place for life, or won't be in the future.
So we talked about the universe is expanding, and it's speeding up in its expansion. Now, you might be tempted to believe that this room is expanding, but it's not. This is a special part of the universe. It's a part of the universe which is 30 orders of magnitude more dense than space. And so this part of the universe collapsed to form the Milky Way, it formed Earth, all those things billions and billions of years ago. So we sort of nucleated out of the expanding universe, and every galaxy is one of those little nucleides, and it's the space between us that is expanding. Well, that's not completely true, because galaxies form in groups, and the nearest big galaxy to us is the Andromeda Spiral, very similar to our own, and it turns out it's one of the few galaxies that's coming towards us. Why is it coming towards us? Because of mutual shared gravity, and the little sphere around us actually has more stuff in it than the average of empty space, and so our little part of the universe is not expanding, it's actually collapsing. And we're going to have our own little Gnab-Gib, which is the Big Bang in reverse, in about 4 billion years.
4 or 5 billion years. It's heading at us, straight at us, about 100 kilometers per second.
No, 230.
230. Well, I'm a theorist. That's pretty good.
You know, it's order of magnitude. That was correct.
But here's what it would look like, in fact, as it gets closer, in 3.7, 4 billion years. That galaxy is heading right at us, which you might imagine is a terrifying thing. In 6 billion years, what will happen, however, is it won't be so catastrophic, because there's so much space between stars in our galaxies that even when the two galaxies collide, almost no stars will hit any other stars. It'll just merge together to form one big galaxy. So if we could be around, we'd just be looking at this galaxy. But this image is very deceptive, because the Earth won't be here in 6 billion years. Our sun, as Brian said, is going to get, in fact, in about 2 billion years, it'll be 15% brighter. And that means Earth will no longer be in the habitable zone. The oceans will evaporate. There'll be a runaway greenhouse effect, whatever we're doing to help it. At that point, it'll be a runaway greenhouse effect. The surface of the planet Earth will be about 1,000 degrees. It'll be just like Venus. It will not be very hospitable. Unless we move the Earth, by the way. It's actually quite easy. But it doesn't matter, because even if we move it a little bit, in 5 billion years, when the sun burns up all its fuel, it will increase in size, and it will be so big that the Earth, in its present orbit, would be inside of the sun. So we will literally be toast. So we won't be around to see it. And the question is, will other civilizations be around? Maybe, but it turns out in the longer time, it's even worse. The future is miserable in the extreme. Because as much as the sun wants to kill us, and galaxies are going towards us, the universe is getting worse and worse. If we look at the galaxies we can see today, as Brian pointed out, there are regions further away than where we can see today, where there could be galaxies that we'll never see, because they're expanding away from us faster and faster. But if the expansion of the universe that Brian discovered continues, then these galaxies will eventually be moving away from us faster than the speed of light. And eventually, if we wait long enough, the entire rest of the universe will disappear. So astronomers in 2 trillion years, if they're astronomers, and the lifetime of the oldest stars will be longer than that, will in fact look out and think they live in the universe we thought we lived in 100 years ago, with a single galaxy surrounded by eternal empty space. But eventually, even that'll get worse, because our stars will burn out, They may collapse into a massive black hole, which we think will happen, which may then evaporate, and the universe will become cold and dark and empty. And that's the future. So the point that we've tried to tell you here are two things. First, the universe is unfathomably big, and therefore you are unfathomably insignificant. The second thing is the future is miserable. So you are insignificant, and the future is miserable, and that's what you should take away from this presentation. Thank you.